All right, good evening, and welcome to lecture 23 for MT225. Tonight we're going to be taking a look at shear stress. Last time we looked at normal stress and normal strain and got an introduction to the ideas of Young's modulus and the spring constant, Hooke's law, and we'll review a little bit of that at first, but we're going to jump into shear stress and look at how we define that. Similar definition to normal stress, but the areas are a little more complex. So in one regard, it's a little more challenging to handle than normal stresses. But on the other hand, there are some simplifications. For example, we don't have to really worry too much about shear strain. So tonight we'll take a look at shear stress. A few administrative notes first. First off, homework 9 has been posted. Homework 9 is due next week. So homework 9 is a little bit of practice on both normal stress and strain and on shear stresses. So you'll get a chance to look at some of those. Probably will find this homework assignment to be a little bit simpler than some of the ones that we've worked on. In fact, the amount of time you might likely have to put into it will be significantly less than those assignments that have involved analysis of structures. Like I mentioned last time, we've kind of passed the peak level of difficulty in the course, and we've essentially started a new course, Strength of Materials. So last time, see the schedule from lecture 22. We've got next week is our last full week of regular class. The week after that, we'll be doing our third exam, and the week after that will be our last week and our final exam. Schedule details are in lecture 22's video. So today we'll review a little bit on normal stress. We'll take a look at the basic concepts, and I'll write down the basic equations that we learned last time. And then we will take a look at shear stress, and we'll define what shear loading is and how we can count up the area that's involved in shear stress. So a little review of normal stress. So in normal stresses, we had a force applied typically along the length of a structural member or beam. It had to be a uniform distribution of force. So the basic picture that we used looked something like a beam loaded in, let's say, tension with some amount of force, let's say 10 kips. Definitely in equilibrium. If we slice through that at some point nearby the middle of the beam, far away from the ends, and we zoomed in on the forces that were acting on that surface. So we zoom in on that cut. What we would see is not one force pulling to the right with 10 kips. What we would see is a uniformly distributed force that, if we added it all up, would equal 10 kips. But that 10 kips is spread out over the cross-sectional area. So last time we learned how to calculate the normal stress, which is essentially a pressure. And as a pressure, it's a force spread out over an area. Here, the area is the cross-sectional area of the beam. So it's what you'd see if you cut through this and then turned it so you could look end on at the beam. That would be the exposed area. And the normal stress, we gave this funny looking little character the Greek letter sigma, and it's equal to the force over the area. And sigma is positive if we have a tensile force, and it's negative if we have a compressive force, just by convention, by agreement. So that's normal stress. Then we looked at the response to stress. We saw that materials tend to expand when they're put in tension and tend to contract when they're put in compression. So we saw normal strain. Normal strain involves applying a force to something and measuring how much it elongates. So when we've got our structural member loaded, it stretches out by some amount. That amount we call the elongation with this funny little Greek letter, delta. Delta, if we spread that out over the entire length, so we think about what each little piece has to grow by in order to eventually end up being longer by delta, we got the normal strain, which is using the little symbol, the symbol lowercase epsilon, another Greek letter. So epsilon is delta divided by L. That's our normal stress. So we had our normal stress and we had our normal strain. These are the basic definitions. So any problems that come up involving normal forces, forces perpendicular to the surface, and that's exactly what we've got here. We have a set of forces perpendicular at 90 degrees to the surface. That's what normal stresses cover. Any problem involving normal stresses or normal strain can be figured out typically by these basic equations. So it's just these simple three-part definitions. Sigma is F over A, epsilon's delta over L. There is a connection between the stress and the strain. The stress causes strain, and there's a proportionality between the two. So if we have more stress, we have more strain. If we have less stress, we have less strain. So these two are definitely on the same level. It's not an inverse relationship between them. It's not like one goes up and the other goes down. But there is a proportionality here. And the proportionality constant we called Young's modulus, or the modulus of elasticity, and it connects together stress and strain. It's a big, big number, millions. So that means to get typical stresses, we're only going to have a very small amount of strain. It's very common to have strains in the thousandths to millionths to get normal stresses that are typically in the tens. So it's a Young's modulus is a very big number. That means the strain is a very small number. And if we turn it around, we can see that, because if we solve it for the strain, it's the stress divided by the modulus. So we're dividing by a really big number here, so we end up with a small number. So that we called Hooke's law. And that's the connection between stress and strain. We'll see a little bit more on Hooke's law next Monday night when we start looking at the strengths of materials. So when we look at how materials really behave, they do tend to follow Hooke's law as long as the stresses are below a certain limit. Once the stresses go above that limit, the proportionality changes. It's kind of like how I showed most of you in basic electricity with Ohm's law. When I hook up a resistor to a power source and I measure the voltage and I measure the current, the two are proportional as I turn the voltage up. But at some point, the voltage is high enough that the current is starting to do damage to the resistor, and it heats up and starts to smoke and eventually bursts into flames. That's not covered in Ohm's law. Just like breakage is not covered in Hooke's law. Hooke's law says we can pull on this as hard as we ever want to, and it'll just strain a proportional amount. But in reality, we know we pull on things too hard, they eventually break. So there's got to be a limit somewhere. There's a physical limit somewhere. And we'll take a look at that on Monday night. So that's a little bit of review on normal stresses and normal strains and Hooke's law, the modulus of elasticity. I do have to say a word on units here. You have to stay consistent between the units that you use for stresses and for Young's modulus. If you're using stresses in KSI, then you have to have your Young's modulus in KSI also. Otherwise, you end up being off by a factor of 1,000 or maybe even a factor of 1,000,000. If you use stresses in PSI, then your Hooke's law or your Young's modulus has to be in PSI also. You have to keep consistent with it. I can also say something about the units with respect to strain. Strain technically has no units to it. We looked at it as inch per inch, thinking about how much larger each inch would have to get, but it actually works out for any unit that we'd want. So if I've got a strain of 0.001, I might interpret that as 1,000th of an inch per inch, but I might also interpret that as 1,000th of a foot per foot, or 1,000th of a mile per mile. The proportionality works out. Once the units drop out, we can put any units we want in. We have to be careful on the other side of that, though, when we're generating stress or we're generating strain by taking force over area or length, elongation over length. There, the units have to be consistent. So areas, for example, always square inches for our purposes. Otherwise, we won't get PSI or KSI. Lengths, as long as the elongation and the length are in the same units, it's okay, because the strain has to be dimensionless. So if you've got a length in feet, you have to have your elongation also measured in feet. If your length is in inches, then you measure your elongation in inches. So pay close attention to the units. It's a place where you could pretty easily have some problems. So let's look at tonight's content here. Tonight's content, we're going to take a look at how shear stresses work. And so first, let's compare normal stress and shear stress. Normal stress involves tension or compression. That's what we find when we deal with truss members. We have normal stresses because the forces act perpendicular to the surface. If we cut through the beam, we see an area and the force is perpendicular to that area. And that's what the word normal means. Normal means perpendicular. It's a math word for perpendicular. Shear is a little bit of a different story. For the most part, for most people, when you hear the word shear, you might think of things like scissors, shears to cut something with. Well, the way shears work is they push across an area. If we're trying to cut through, for example, a piece of paper, what the shears do is they push one side of the paper up while they push the other side down. That creates a force that is parallel to the cross section of the paper. So in shear stresses, we have loading forces parallel to a surface or across an area. The stress that we deal with when we have a force acting in such a way, we call it the shear stress. So shear stress is measured in a little bit of a different way because the area is measured in a different way. If we take a look at the board here, we can see how that works. So let's set up a shear stress situation. Let's take something that's pretty familiar to most people in this class. We'll look at using the sheet metal shear. That's something you've mostly all done. And in the sheet metal shear, you've got a block underneath. That's what supports the piece of material that you're trying to cut. And then you've got this blade or block that comes down. And although I've drawn it kind of badly here, it's a little bit offset. So there's some space here. There's a gap right there. Well, this pushes down with some amount of force. And as a result, to support this, if you imagine putting the top block, pushing your foot on that pedal till it just makes contact and you're pushing hard, you're pushing on it, but you haven't really cut through yet, the whole system is in equilibrium, which means the same force must be pushed upward by the tabletop on the sheet metal shear. Well, if we zoom in on this area right here, this area that we know is going to break when you push the sheet metal shear pedal down, if we zoom in on that, what it looks like is we have this long area here. That's the sheet metal. So we got our broken line here. So that's the sheet metal right there. And the force is spread out over the area that way. Look at how that's different than the normal stress situation. In the normal stress situation, we were perpendicular to the area. Now the force is parallel to the area. Another example, and one that will work out a little bit more to illustrate shear loading, is to imagine just taking two pieces of metal and gluing them together. If I take a piece of sheet metal this way and another piece here and form a lap joint, but I've put sealant all in this area, or glue and adhesive all in that area to stick those two parts together. If I pull in this direction and pull in that direction, this is in equilibrium, which means if I were to draw a free body diagram of, say, the lower piece is free body diagram, I'd still have the force to the left, but what I'd have in that area where the glue is I'd have a little distributed force parallel to the surface. That's normal stress. That's shear stress, excuse me. And the shear stress is along the surface. So the hallmark of a shear stress is that the shear stress is along a surface or across an area instead of perpendicular to it. The definition is essentially the same as with normal stress. To avoid confusion, we use a different symbol. We call it shear stress, S with a little subscript S. And it's equal to the force divided by the area. But you've got to be careful about what area you're talking about. The area is the area the force acts on. So in this case here in our lap joint, we have some width of this joint and we have some length of overlap. We could use that to figure out an area. Whatever force we're using would be spread out over that area. It's not necessarily the cross section of the pieces that you're working with. So you've got to be really careful about counting area. And a good trick that I've learned about how to count the area is to use your intuition a little bit and kind of imagine what it's going to look like when it breaks. If you pull on these two pieces hard enough that this joint between them breaks, then you'll be able to see that area where the broken glue is left behind. And I think we've all had experiences at some point in the past where we've pulled on two parts and they were only glued together and they came apart, and you could see the residue of the glue behind. That's what area was resisting the force in shear. If you look at that area that broke, so the two parts could go away from each other, that's the stress. That's the area that the stress was exerted on. If you look at our example for shearing sheet metal, think about what this is going to look like broken. When it breaks through, we're going to have some rectangle of area exposed. We'd have the end of that sheet metal, whatever thickness it is and whatever length of metal we were working with, that's going to be the part that breaks. We're going to be breaking right through the material, and that's the area to use for our shear force, or for our shear stress. So we'd take our force divided by that area. So the area that you need to look at is typically the area that's going to break if we overload that connection. So when we generate a force parallel to a surface or across an area, we have a shear stress. Now, shear stresses are pretty important. In a lot of situations, they are very important to, and in fact, can be more important than normal stresses. They are on equal footing for the most part. And in aircraft, especially, we deal a lot with shear stresses because that's the force that rivets handle. So in an aircraft, when we do lap joints, for example, we're not really worried about holding the sheet metal to the surface. We're worried about shearing happening, the sheet metal shearing against whatever structure it is enclosed in. Same thing comes up in building construction. If you think about building a wall, and if you've had some practical experience out there building things like 2x4 walls, you may have had situations like this come up where if you've gone and built a wall, say we've got this 2x4 wall. So we've got some 2x4s here, and not necessarily to scale, but we've got a typical, maybe a curtain wall, or maybe if the pieces are spaced closely enough, maybe we have an exterior wall, load-bearing wall, top plate, bottom. There we go. So we got some wall like this. Well, if you build one of these things, that it's usually because we're putting stuff down on the top. We're putting forces down on the top. That would be a compressive load on these members. But if we're not careful, sometimes we can get loads acting like this. Like if somebody comes in and tries to move this and they push at the top, I think you might be able to visualize what happens to it in a typical wall like this. If you're not careful, it does what we call racking, where instead of being a nice rectangle, it goes to something that looks sort of like that. And if that kind of motion gets going, if there's nothing to stop it, it can collapse. If you've got a lot of load on top and this shear loading starts happening and you get this racking action going on, then the weight that's on top can just keep driving this and it'll eventually fail. You might have seen even situations where somebody's got a roof structure put together, they've got they've got load on the structure, and maybe wind pushes things over to the point where the whole structure collapses. Well, we avoid this by putting in panels that can resist shear. You might put in a piece of wood across like this. That will keep this from racking. Another thing to do is put a piece of plywood there. Put some plywood sheathing on there. That plywood sheathing acts as what we call a shear panel, which prevents the whole structure from racking. So that's another example of where shear forces can come in and some of the problems that can be caused as a result of shear. So so it is an important force. It's something that we definitely have to take into account. So here's an example of shear stress, and we'll put some numbers on this one. Let's say we've got this glued lap joint. The force that's trying to pull those joints apart is going to be distributed over the whole contact area, and that will be our shear stress, the force spread out over that contact area. So let's see how it looks. So let me first redraw this with a little bit of geometry on it. Let's say we've got this lap joint, And we'll put, let's say, 10 kips on it. Now this joint, I'm going to make the overlap in this lap joint, say 2 inches. But if I had a top view of this, it would look something like this. Top view, because to find the area, we have to have 2 dimensions. We'd have a line right here. Little drawings review, got to have a hidden line there. And let's say this width, the width of our lap joint is, let's say 4 inches. Now the surface that is supporting, and wow, I was looking at the camera and not the display. Let's move the hidden line over here. There we go. Yeah, that's a little better. Looking kind of an angle on the document camera. So there's our overlap. Now the area that has the glued joint, the area of that glued joint is right there. So we can assume it's not a perfect situation, but we can assume that it's close enough that this 10 kips is spread out uniformly over this area where all the glue is. If we've spread the glue out nice and thin and evenly, we'll have a pretty much uniform distribution of force. Well, that's a rectangle. The area is 2 inches by 4 inches. The area involved here is 8 square inches. So our shear stress is 10 kips of force. It's the force spread out over the area. So it's 10 kips of force divided by 8 square inches. And that'll give us 1.25 kips per square inch, or KSI. Now that 1.25 KSI, that would be something we'd have to check with the glue manufacturer and see if that's a shear stress that glue can handle. We could figure out some information about that to try to make sure that this thing isn't going to come apart. If this is a design we're working on and we think we're going to be able to hold 10,000 pounds on this 4-inch by 2-inch area, it might be worth our while to go and check and make sure that it can actually handle that stress. So that's our shear stress. Now, a glued joint isn't the only way to do this. We could create a lap joint by, instead of using glue, we could use a pin. And if we use a pin, we have a little bit of a different situation. So let's see how that would look. Let's say instead of using glue where the whole area of the joint supports the force, let's take the same situation, 10 kips. Instead of using the whole contact area here, we're going to put a pin in. So we'll put a pin through here. So that pin is going to join the two parts together. And so that pin, we'd have to have hole drilled through, and then we'd have to drive that pin in. So the top view might look something like that there. Now that pin has a certain diameter to it. Some diameter D. And if we imagine how this would look if we pulled it until that diameter broke, you can see that we're loading that pin in shear. It's going to cut right across the diameter. If we pulled it hard enough to shear through, then we'd have half of this pin on one side and half of the pin on the other. And when we look at the end, we'd see a circular area with a diameter D. That's the area that's supporting our load. We don't have any of the other area here supporting the load because there's nothing there to hold these two together. They're not really in contact. Friction's negligible, so we don't really have something that is in direct contact or held together there. So if we put some numbers on this, let's say this is, again, the same diameter, same dimensions. Let's make this a 2-inch lap with a 4-inch width. And we'll make this pin, let's say the pin's 3/4 of an inch in diameter. So diameter is 3/4 of an inch. Well, let's see what the stress is. To find the shear stress, we need the force spread out over an area, the area that is supporting the force, and that's the cross-sectional area of the pin, because that'll be what we cut through if we pull hard enough to break through the material. So that's our shear stress, force over area. We need to calculate the area. Area of a circle is pi r squared, or if you like working with diameters, pi, well, it's quarter pi d squared. Either way works. So you go over to your calculator and figure out the area. So if we use, I like using radius, so I'm going to take my 750 and divide it by 2. I'll square that and multiply by pi. And I get 0.44179. So 0.44179 square inches. And I'm keeping arbitrarily here 5 sig figs. Well, that's my area. My force was 10 kips. So my shear stress is 10 kips divided by 0.44179 square inches. That's 22.635 KSI. Kips per square inch. Now, most materials have a tabulated ultimate shear strength. They have a certain maximum value for stress that they can handle in shear before they break through. And so the shear stress is going to be important to check against that limit. If we want this joint to hold, then we better be using a pin that has a material that is stronger than 22.635 KSI for the shear stress, for the ultimate shear stress. So that's another way we could do the lap joint. We could use a pin to hold that joint together. And we'll see another example of what we can do with a lap joint here in a little bit. So that's shear stress in a lap joint. So just like with normal stresses, shear stress is a pressure. Here's where the equation is in the notes. Shear stress is force over area. Be very careful about what area you're talking about. So be careful about what area is used. Glue example, pretty straightforward because that whole contact area was holding the surface together. So it's just simply a rectangle. So to correctly calculate the stress, we have to look at the area that resists that shearing action. So here's the pin example. In that example, the areas where the pin isn't making contact, those don't provide any resistance to shear. It's just shearing through the pin. So if we have two plates held together with a pin or with a bolt, bolt is just another way of saying a pin. We're using the shear diameter, the diameter of it against shear. Bolt just has a head and threads on the nut side. So the pin would work the same way, but we have to just have the right area. Another example to kind of illustrate the point is to take a look at something we call a punch. Now this is a circular punch or a knockout punch. This is used in things like instrument panels to poke holes, electrical boxes. You can poke holes in those to create passageways for wires and such. Viewed from the side, we can see here that we've got three solid pieces here. This is a support block that's underneath, and we're looking at this sort of in cross section. I'll draw a top view of it on the page here. Up here at the top, we've got a die, and that die has force applied to it. The metal we're working with, or the material we're working with, is here. So this would be a piece of sheet metal sitting on the die and on the support blocks. So let's look at what this would look like. So here's the front view. We've got a support block. We've got the other side. We've got our sheet metal piece. And then we've got our die. So the die is undersized just a little bit. It's just inside the diameter in the support block. So that's our die. Now the top view of this would look something like this. I'll try and get the sizes to kind of match up here so it looks pretty reasonable. So we have this bottom part. This part here is the bottom support, and typically that support would have a hole in the middle of it, and I went and drew the hole the wrong size here. So let's try that again here. So the hole is going to be something closer to that. That's the hole in the bottom plate. Then we've got our piece of sheet metal on top. And then we've got our die sitting right here. So the die would be pushed down and it would break through there in a circular shape. And it would leave a little slug of material that it punches out. And then there'd be a ring of broken material. Here we have to be very careful about calculating the area that's resisting shear. And you can use that trick that I mentioned a little bit earlier. The best trick I know to figuring out the area is to imagine it broken. Imagine what it looks like after. What's the new material that's been exposed? What did it break through? Well, the area that it broke through is this cylindrical area. It's the cylinder that's the thickness of our sheet metal high and the diameter of our die wide. So let's say this is a 3-inch punch. 3-inch punch would have a diameter on the die of 3 inches. And we've got some sheet metal. Let's pick a typical thickness sheet metal that we might use, maybe 63 thousandths. Well, remember how to find the surface area, the area of a cylinder, not the volume of a cylinder, but the area of a cylinder. The area of a cylinder is pi r squared 2 pi r, the circumference of a circle, times the height. So it's 2 pi r, the circumference of the circle, so the distance all the way around that big circle, times the height. So imagine stacking up rings like a slinky. Those rings each have a circumference. You stack them up, you get an area, you get a surface area. So you get a ring shape. So let's figure this out here. You got 2 pi. The radius is 1.5 inches, and the height is 0.063 inches. So the area for this cylindrical knockout is 2 times pi times 1.5 times 0.063. So the area comes out to be 0.59367. The units, inches times inches, so square inches. So a little bit more than half a square inch. So let's find out the shear stress. Let's push down here with, let's say, 5 kips. If we push down with 5 kips of force, the shear stress is the force over the area opposing that force. So we have 5 kips, 5,000 pounds of force, divided by 0.59367 square inches. And that gives us 8.4209 kips per square inch, KSI. So not a whole heck of a lot of stress, shear stress. So that 5,000 pounds may not be enough. Because in this case, unlike the case with the pin where we wanted to make sure our stress was not above the shear stress of the material, the ultimate stress of the material in shear, here we're trying to break it. So we can use this to tell us, well, will this break? And how can we change things to make it break? Well, we can push it we push it harder. If the ultimate shear stress isn't until 10 KSI, maybe I need 6.4 or so, or 5.4 kips to do the job. So I may need more force or less area. Maybe I got to use thinner sheet metal. Maybe this punch isn't designed to work on 63 thousandths. Maybe it needs 40 thousandths or 25 thousandths. So the stress can be used to evaluate lots of different situations. Will it break or won't it? Is a good one to look at. So that's what shear stress is all about. So there's a punch. A cylindrical shaped area is holding against the force, so we'd have to go and calculate that out. Now, when we looked at normal stress, the next thing we looked at was strain. I had said that whenever a force is applied to a material, that material responds. If that force is tensile, then the material responds by expanding. If the force is compressive, the material contracts. When we load a material in shear, there's a response as well. But that response is a little bit different than it is for normal stresses. So when we apply a shear stress, what tends to happen is things tend to change shape. But they don't change shape by expanding or contracting. Instead, they change shape so that angles change. Take, for example, here this box that's shown on the screen. While normal stresses cause shrinking or stretching, shear stresses cause an angular change. So think about that racking wall example. When I apply a shear stress to that, it changed from being a rectangle to being a parallelogram. The angle essentially here changed from 90 degrees to something smaller or something bigger than 90 degrees. That's what happens with shear. So when something's in shear, we expect angles to change. And angles are kind of a pain to measure. It makes it so that shear strain really isn't as useful as a normal strain is. Shear stress is much more useful than shear strain, just like normal stress is typically much more useful than normal strain. But as far as stresses go, shear stress is much more important than shear strain. We don't really bother measuring angles. This can be used in some cases, and in fact, in some cases, it is used to measure loads on things. We have what's called a strain gauge, and some variations of strain gauges work by measuring these angles, by changing their values as the angles change. Most of them work by using expansion or contraction. In a strain gauge, as it expands, its resistance becomes bigger, so we can electrically detect tensile stresses. And that's what's outfit on a lot of aircraft today. They put those in all sorts of critical places so the computer can measure how much stress the aircraft was under. So strain gauges work very well for that. So shear strain does have a proportionality, just like normal strain was proportional to normal stress through Hooke's law. Shear strain is proportional to shear stress. There is essentially a modulus of elasticity, but in strain instead of in shear instead of in normal. So we have a modulus of elasticity in shear, or a shear modulus. That's the constant of proportionality that measures angle change versus the amount of shear stress. So it is a measurement of reaction essentially to shear stress, but it's not terribly useful. So we don't really bother doing at this level any kind of calculations with it. So let's take a look at a couple examples here. Now, I've done a couple examples already for shear stress. So let's look at one that's a little more common to working with sheet metal in aircraft repair. Let's look at a lap joint. But in that lap joint, we're not just going to use one big pin. We're going to use a bunch of small pins that we know as rivets. So let's take a look at how a riveted lap joint works. So in a riveted lap joint, I'll draw the top view first here. We've got two pieces of sheet metal overlapping each other by a certain amount. And those of you who have been through the sheet metal class, you may be having flashbacks to going to the 4313, going into the W tables and figuring out what the overlap was and how many rivets to use and all that stuff. And we'll get to where that table comes from next time as we look at design problems. But we've got this overhead view, or this top view. The side view is going to look something like this. We've got our bottom piece here. And our top piece there. And we're going to hold this lap joint together with, let's say, 5 rivets. So 5 rivets. And we're going to use the typical common rivet, the AD rivet that we use, most of the AD rivets we use are 1/8 inch diameter rivets, 84s, so 4/32 or 1/8 inch. So we'll do 4 1/8 inch diameter rivets, 5, excuse me, 1/8 inch diameter rivets to hold this lap joint together. So those look kind of like those pins that I drew earlier, except they're going to have rivet heads on them. And we're going to form a shop head down here. So we're going to have 5 of those holding this structure together. So let's put some numbers on it. Let's pull on this thing with, let's say, 20 kips. Now, if we think about the area that is resisting that 20 kips, think about what it'll look like broken. To have these two parts separate from each other, all 5 of those rivets are going to have to shear through their diameter. So to count up the area, we have to count up the area of all 5 of the rivets together. This would be mathematically equivalent to using one big pin with the same area as these 5 rivets together. And in fact, structurally, in principle, we can do that. But it's better if we spread that load out. So what we really do when we're going into those W tables and such, what we're really doing is we're finding the area of the pin we need to handle that force. And then we just split it up into a certain number of rivets. So when it says use 12 rivets for this lap joint, well, then that means that 12 rivets is enough area to hold that joint together. So let's figure it out for this one. Let's make this it seems like all these lap joints are 6 inches wide for some reason. So we'll make that 6 inches wide, and we'll, let's see. Yeah, be careful about extra information. You know, I might tell you this is 40 thousandths thick material, and maybe there's an overlap of 2 inches there, but be careful of what you need. To find the shear stress, you need the force that's applied and the area that supports that load that's stopping these two things from coming apart. So let's figure out the area. Now, whenever I've got rivet problems, the first thing I like to do is figure out the area of one rivet. So I'll write area with a little subscript 1. That tells me the area of one rivet. And then once I'm confident with that value, I can just multiply it by the number of rivets I've got. That'll give me the total area. So one rivet here, we've got a diameter of an 1/8 inch. And when this shears through, it's going to look circular. So it's the area of a circle. So the area of a circle is pi r squared. And if we plug in the numbers for an 1/8 inch diameter or an 1/8 inch diameter rivet, we've got pi. And we've got the radius. Radius is 1/2 an 1/8, so that'll be a 1/16. And we can square that and multiply it by pi. And so we get a fairly small amount of area. Don't slack off on your sig figs here, because if you rounded this down to 0.012, you've lost a lot of information. Remember, we don't start counting to that first non-zero digit. And that's especially important to remember as we're dealing with much smaller numbers. So that's the area of one rivet, 0.012272. Well, I've got 5 of them here. So the area of 5 rivets is 5 times the area of one rivet, which is 0.061360. square inches. So that's our area. The shear stress then is our 20 kips of force divided by 0.061360 square inches. So if we divide that by 20, or divide 20 kips by 0.061360, we get 325.95 kips per square inch. Now that's pretty high. In fact, quickly looking at my handy dandy reference table for aluminum alloys. Now, you know, or can go and look up or should review what alloy we're dealing with our most common rivet, with the AD rivet. But we'll get some ballpark figures here for the ultimate shear strengths for these rivets. So for aluminum, let's say for 6061, which is a pretty strong aluminum alloy, the ultimate shear strength is only 27 KSI. So here I'm loading this up to 329.95 KSI, which means these rivets are going to shear through, and I'm going to have a broken airplane. The shear stress is too high. And whenever the stress is too high, we have two choices. We can either reduce the force, or we can increase the area. Now, reducing the force may not be an option. This may be the load that's imposed on the aircraft, and our task is to figure out how do we patch this so that it maintains the correct loading. So the other answer is to adjust the area. So maybe an 1/8 inch rivet's too small. Maybe we can go to more rivets. If an 1/8 inch rivet, if 5 rivets didn't do it, maybe 20 rivets would do it. So we could go and find out, well, what's the area of 20 rivets? Well, that would be 20 times the area of 1. So the area, so let's say I'm stuck using 1/8 inch rivets and I've got 20 of them. 20 times 0.012272. That's 0.24544 square inches. So my shear stress will drop from 329.95 to 81.486 KSI. Well, it's a step in the right direction, but it's still pretty high. In fact, looking through my table here, the only thing that I readily see available that has a shear stress above, an ultimate shear stress above 81 KSI is titanium. Titanium has 100 KSI for its ultimate shear strength. So unless we're using titanium rivets, then we're in trouble with this. So maybe we go to 40 rivets. Well, if we double the number here, we kind of expect half of the stress. If you double the area, half the stress, 40 rivets wouldn't even do it. And it may be getting awfully crowded in this 6x2 inch lap joint to try to drive 40 rivets in there. So maybe we don't use 1/8 inch rivets. Maybe we use, let's go to 5/32 rivets. One size up. Well, let's see where that puts us. If we go to a 5/32 rivet, the area we have 5/32 divided by 2. squared. We get a little more area, 0.019272 square inches, 0.019174. 20 of those would be 0.383 for 38350. And if we put 20 kips on that, we're down to 52 KSI. So maybe a 432nd rivet or 532nd rivet isn't going to do it. So maybe we need a 632nd. So let's try a 632nd here. If we go to 632nd rivet, well, the area of one of those is 0.027612 square inches, and 20 of those is 0.55223. And that gets us down to 36 KSI. Now that's above some alloys. Copper, it's above copper. It's above, copper would work because copper has an ultimate shear strength of 38 KSI. Cast iron at 38 KSI. Brass at 50 KSI. We're still not quite down into the aluminum neighborhood here. So maybe we need, let's go full on to a quarter inch diameter rivets. Haul out the big guns and the big rivet sets. And we'll do 1/4 inch diameter rivets. Well, 1/4 inch diameter rivet has one diameter, or one area, area for one rivet is 0.19635 square inches. Well, let's try 10 of those and see if that'll work. That looks like it might fit within 6 inches. 10 rivets, 1/4 inch diameter each, probably going to be okay with edge distance and pitch there if we do transverse pitch. Well, that's an area of 1.963. So if we're doing 20, or if we're doing 20 kips of force, that's 10.2 KSI. So that'd work. We might even be able to go down to 5 rivets. If we do 5 1/4 inch rivets, 0.19635 times 5, that gives us a shear stress of 20.371. So 5 1/4 inch rivets would do it, and would do it within the limits. So aluminum alloys are typically in the 20s, higher 20s for ultimate shear strength. So looks like it would work. And this is a little bit of a preview of kind of how a design problem will work. Now we can be a little more accurate about this and turn the problem around and say, if we know what the shear stress needs to be at maximum, what's the minimum amount of area we can get away with? And then we can say, well, if we know that area, then we can figure out how many rivets we need. But that's how rivets really contribute strength to a joint. They are providing area for shear forces to resolve on. They handle that area because they can handle that force because it can handle shear stress. And the number of rivets we've got depends on the amount of stress that we need and the amount of force we need to be able to produce the amount of area that we need to support that force. So that is the basic idea behind shear stress. So at this point, you should have a pretty good handle on shear stress and area and how all that plays together. And so now we know normal stress, and we know shear stress, we know normal strain, and we can go on to do some actual useful work. So next time on Monday night, we will take a look at the strength of materials. We'll learn how to look up and find the limits on material behavior, and then we'll figure out how to design within those limits. It's not that difficult. It's just an idea of looking at areas first. We know the force, we calculate the area based on the maximum allowable stress. Then once we know that area, we can figure out how we're going to distribute it, how many rivets we need, how much cross section we need for our beam, what size lumber we want to go with, 2x4, 2x6, 2x8, 4x4. It all depends on what those stresses come out to be and what our safety factor is. I'll define what safety factor is, and we'll see how that works and how it affects a design problem. I'll also take any questions we have on the homework. So that will be on Monday night. Have a good weekend. I'll see you Monday.